Hello, my name's Timothy Clemson and I work at the Institute of Cosmology and Gravitation at the University of Portsmouth. Cosmology is the study of the universe on its largest scales and over its entire lifespan. So today, I'll be asking, how old is the universe? How big is the universe? And what is the universe made of? Like most people, cosmologists used to think that the universe had been around forever, unchanging. But observations of distant galaxies have shown that in fact, they're all moving away from each other. This means that earlier on in the universe's history, they must have been much closer together, and that far enough back, the entire universe that we can see would have been contained within an incredibly small volume. This point is known as the Big Bang, and is thought to have occurred around 14 billion years ago, which is something like 3 times the age of the Earth. It leads to the question, what happened before the Big Bang? But the answer is that there probably was no time before this, and that time itself just didn't exist until after the Big Bang. Einstein, like most people of his day, originally thought that the universe was eternal and unchanging, while the great astronomer Sir Arthur Eddington wrote that both an infinite past and a beginning of time were equally inconceivable. The truth is that we'll probably never really know for sure exactly what happened at the Big Bang. But whether the universe is eternal, or whether it really did have a beginning, is certainly a pretty amazing thought either way. This is our solar system. The planets, including our Earth, all orbit around our star, the Sun. Even the Sun is very far away. In fact, it's so far that it takes light from the Sun 8 minutes to reach the Earth. Farther out are the stars we see in the night sky, and as we zoom out, you can see that even the hundreds of stars in the constellations are all found within just one small part of our galaxy, the Milky Way. There are hundreds of billions of stars in our galaxy, but amazingly, there are also hundreds of billions of galaxies in the observable universe. We're now going to travel out through a map of the galaxies that astronomers can see with modern telescopes. As we do, we're actually looking back in time, as well as out into space. This is because it takes the light so long to reach us from this far out, even though it's travelling at 700 million miles per hour. So when astronomers look deep into the universe, they're actually seeing the galaxies as they would have looked long, long ago. As we travel ever farther out, we can see some clumpiness in their distribution, where galaxies are being pulled together under the action of gravity. Then we begin to see the clusters and filaments of galaxies that make up the structures of the cosmic web, a vast complex network spanning the largest scales of the observable universe. Not every part of the sky has been mapped, but the farthest objects we can see are from where the universe was only 5% of its current age. Finally, we'll reach the deepest we can ever see. This is the first light that escaped from the boiling plasma of matter and energy soon after the Big Bang, about 14 billion years ago. Due to the expansion of the universe, however, this light has actually come from 50 billion light years away. So the universe is at least 50 billion light years across. But could it be even bigger? The answer is yes, a lot bigger. The density of the universe determines what is known as its geometry, which is the underlying structure of space and time. By looking at the light from the early universe, we can learn about its geometry and tell whether the universe is finite or infinite in extent. The average size of variations in the light depends on the path it takes to get to us, which in turn tells us whether the geometry is open, flat, or closed. If the density is greater than a certain critical density, then it's closed and the universe has a finite size, while open and flat universes are infinitely large. Satellite measurements have shown with a good accuracy that the observable universe's geometry is very close to flat. This strongly suggests that our universe is infinitely large. But in the same way as the surface of the Earth looks flat while actually being curved on large scales, it may just be that we can't see far enough into space to be able to measure its curvature. In fact, because the universe only has a finite age, the only thing we can really be sure of is that it's certainly much bigger than the 50 billion light years across that we can observe. When astronomers look into the night sky, they see billions of galaxies, each containing billions of stars. But recent observations have shown that there's more to the universe than meets the eye. We now think that most of the universe is comprised of what are called dark energy and dark matter, with only a small part being made up of ordinary stuff like you and I. The discovery of dark energy came about from the study of exploding stars called supernovae. These can be nearly as bright as entire galaxies of stars, allowing us to see them far out into the universe. By looking at a particular class of supernovae called Type 1a, which all explode in a similar way, we've been able to measure how the expansion rate of the universe has changed over time. It turned out that instead of slowing down due to gravity, as was expected, the expansion of the universe is actually speeding up. We can't yet be sure of why this is, but the consensus view among cosmologists is that it's caused by the cosmological constant, an innate property of space-time counteracting the force of gravity. It was first talked about by Einstein in the early days of cosmology, but proved impossible to measure until now. Dark matter, however, has been known about for much longer. This is simply because the orbital speeds of stars around their galaxies imply that there must be more mass present than that we can see. More recently, by studying the way its gravity bends the light from distant galaxies, we've been able to map the distribution of dark matter around clusters of galaxies. And computer simulations have shown that without dark matter, the universe would not have formed the structures that we observe in the distribution of galaxies. The precise nature of dark matter is still a mystery. It's widely believed to be some new type of particle, but detection experiments around the world have as yet failed to provide conclusive evidence as to exactly what it might be. Finally, pinning down the nature of dark matter will be hugely important for our understanding of the world around us and of the universe as a whole.